So today we discuss electromagnetic induction, the new chapter here, and here's the new concept, induction. Okay, electromagnetic induction. Induction. Okay, the new chapter of electromagnetic induction. So here we know that a moving charge produces a magnetic. Okay, moving charge means the current carrying wire. Okay, produce a magnetic field. We know that the concept from previous chapter, previous classes. Okay, we know the concept that moving charge means current produce magnetic field. B. Okay, moving charge produce magnetic field. Now then one question arises here, but conversely effect is possible. Okay, so magnetic field produce current. Can magnetic field produce current? Answer is yes. Magnetic field produce current. Okay, that's possible. Yes, answer is yes, possible. Okay, in England, Michael Faraday, and in USA, Joseph Henry. In 1830, they experiment and they satisfy that these reverse possible, like these are the reverse, is conversely possible, is possible. Conversely effect is possible. Okay, they found that current generated by the varying magnetic field. They found Faraday and Henry. Okay, and Henry in 1830s, they found the magnetic field. They found that current generated by a varying magnetic field. They found current generated by varying P. Okay, like moving charge produce a magnetic field. Okay, the varying magnetic field produce a current. This conversely is possible. Conversely effect is possible. Okay, and they show some experiment, and they're doing some experiment and get that direct conclusion. So suppose that in experiment number 1, there is a coil. There is a coil. There is like a solenoid. And that's a galvanometer G, and that's a bar magnet north, and that's a south. Okay, and that's a magnetic field. Okay, and you see that very carefully. When bar magnets moving, these are the bar magnets. Bar magnet is moving towards the coil. When moving towards the coil, and that here the current is generated. Okay, and is produced. Okay, these are the I. And when current is generated, the galvanometer is deflected. Okay, when bar magnet towards the coil or bar magnet away from the coil, there is a current is generated here, but they are in opposite direction. So galvanometer deflected in opposite direction. Say that is when bar magnet moving towards coil, the galvanometer is deflected. means the current is produced. Okay, towards the coil, and if a bar magnet away from the coil, away from the coil, so galvanometer also deflected. Galvanometer also deflected, but in opposite direction. Okay, so do both cases, when bar magnet is moving towards the coil or away from the coil, we get some current here. But when bar magnet are stationary, okay, so there is a no deflection. When bar magnet in stationary, so gets no current, because here discuss here, okay, the varying magnetic field, okay, means a very important concept is a varying magnetic field. Okay, that's the key point. The varying magnetic field produce a current. Okay, keep in mind, varying magnetic field. When bar magnet are in stationary, so magnetic field is not changed. Okay, so B is not changed. When B is not changed means no current. So B not changed means no current. Clear the concept. Main thing is that B must be changed. That's why I get current. And one thing keep in mind, that the direction of the current. Okay, the direction of the current. Actually, here we ignore direction of current. Of current. Okay, because the direction of current defined by the Lenz's law. When we discuss the Lenz's law, then we discuss what is the direction of the current here. But here we only discuss that current is generated when bar magnet is moving towards the coil or away from the coil. Okay, that's the first conclusion. Okay, and when I replace this bar magnet, or when they experiment number 2, then replace the bar magnet replaced by a coil, another coil. So okay, so there is a coil. There is a galvanometer. Okay, suppose there is a coil number 1. Okay, and here is another coil. Uh, Suppose this coil is connected a source. Okay, and now this coil 2. Okay, when this coil 2 are connected to a source, power source, so there is a current direction. Okay, okay, so that's the direction of the current. Okay, when you get a direction of the current, so this current produce a magnetic field. We know that from previous chapter concept. Okay, produce a magnetic field, and that magnetic field, some part of magnetic field obviously crossing this coil, some. Okay, some part of the some part of magnetic field crossing the coil C1, and when they are in stationary, when they are in stationary or rest, so galvanometer G, that is equal to 0, no deflection. no deflection. Okay, means no current here. So current, because the B is fixed here. B is fixed, not varying here. But when they are in motion, of any one relative motion, any one of them, if either C2 or C1, if any one of them, if any one of these two coils are moving towards that each other or away from each other, then we get some current. Okay, when they are they moving in relative motion, any one of coil C1 and C2 are moving, we get Ig. So galvanometer deflected. If they're moving towards suppose the coil, suppose that's choose the main direction here. Okay, uh, direction, current direction, or away from that coil, so opposite direction of okay. If towards the coil, these are the towards the coil is another direction current. Okay, suppose they are suppose say that is clockwise, and away from the coil, suppose say that they anti-clockwise. Okay, keep in mind that. Okay, here we not discuss the current direction, here we discuss the current is generated, the magnetic field varying current is generated. Okay, but these current, suppose say that there is a current and this current also produce a magnetic field, that magnetic field oppose that magnetic field. Keep in mind. Okay, when we discuss Lenz's law, we discuss that part. Okay, so any one of them are in relative motion. So when we replace the bar magnet via coil 2, replaced by the coil 2, this bar magnet replaced by the coil 2, so we get some current when they are in relative motion. That's keep in mind, when they are in relative motion. If any one are in motion, okay, any one of two coils are in motion, if both are erased, so no magnetic field is fixed. If they are in rest, magnetic field is fixed. So if magnetic field is fixed, so there is no current. Magnetic field is varying when they are in moving. That's why we get some galvanometer current, or called a induced current. Okay, this process called, the whole process called induction. Now there experiment number 3. There's an interesting experiment. In experiment number 3, the two coil, okay, these two coil, okay, those two coil, the coil 2 and the coil 1, that's a key. Okay, suppose the coil 1, and the experiment number 3 is very, very important. Okay, and keep in mind that when they are in stationary, they are in rest, both are in rest, this coil C1 and C2 both are in rest, 1 and C2 both are in rest, but when that key press, just press and show galvanometer, these galvanometer show momentary deflection, just a certain one deflection, just deflect, okay, just certain deflection. Okay, and when press and hold, when key, this is a key, press and hold, so G equal to 0, so no deflection. When just press a very small time, very small time. So galvanometer show a momentary deflection, very small time. Okay, similar case when key off, just off. So G shows deflection, shows opposite side of this momentary deflection, opposite direction. Okay, suppose like this. Okay, so here the conclusion is that when he just press or remove in very short period of time, very short period of time, galvanometer shows deflection. Very short period, galvanometer showed deflection. When the key press and hold, that's very important. So that is no deflection. Okay, that's the important point here. When just on and just off, that time galvanometer show a deflection. On, if I say that on is clockwise direction current, and then off, then galvanometer show the anti-clockwise direction of current. That's a key point. Okay, that if any one of that, okay, is key press on and off, the galvanometer show the deflection. Okay, if you reduce this current is opposite direction. If K is removed, okay. In these three experiments, Faraday and Henry, they show that when the current is generated, actually the magnetic field is varying. Okay, the magnetic field is varying, the induced current is generated. The key point is that the magnetic field is varying, that important field is varying, that varying magnetic field produce a induced current. Induced current. Okay. Now, so here to discuss another concept, there is a magnetic flux similar as the electric flux. Okay, discuss the magnetic flux. Phi B. Okay, so if there is a magnetic field, so there is obviously magnetic flux. Suppose these are the magnetic field B. These are the magnetic field B. Okay, and it choose a surface here. Suppose the surface, these are the surface, and the very small surface here. Okay, so surface in that direction, area, and B in that direction, there is an angle between these two. So get phi B flux, that is equal to B dot A. Okay, the phi B dot A. So finally we get B A cos theta. Due to that dot product, we get cos theta. Okay, and there is a phi B. Oh, there is a integration B dot dA, and these integration on open surface. Okay, the surface is open, not closed. In case of electric field, their surface is closed. Okay, closed surface, but here is an open surface. So the SI unit, of the magnetic flux. So B, we know that Tesla, A is the area, that's Tesla meter square. That's the SI unit. Okay, the magnetic flux. And magnetic flux also a scalar quantity because there is a dot product. Okay, that we get a scalar result. So from vector algebra, so magnetic from vector algebra, we say that the magnetic field, magnetic flux is a scalar quantity, but magnetic field is a vector quantity. Okay, these are vector quantity. Similar the area of the direction. Okay, so now we discuss the very important the Faraday laws of induction. Faraday's laws of induction. Faraday's law of induction. In Maxwell's equation of electromagnetic theory, there are the four Maxwell's equation. First, Gauss's law in electric field. Second, Gauss's law in magnetic field. Third is Ampere's law. Fourth, the Faraday's law. These are the four law. Combine these four law, we get a Maxwell's law. And Maxwell's law, there's a little bit change, slightly change, but when we discuss that EM theory, then that time we discuss what changed. But these four laws, Gauss's law in electric field, Gauss's law in magnetic field, Faraday's law, and Ampere's law, these four laws are combined to get a Maxwell's law. But there is a certain change here. Okay. But keep in mind, these four laws in Maxwell's law. Okay, so Faraday's laws of induction shows that there is a surface and these are the open surface. These surfaces are open, means one-sided open. Okay, suppose the surface is look like okay, surface look like there is a fishing net. Look like a fishing net. Okay, these look like a fishing net. Okay, look like a fishing net. Clear? And this fishing net, actually the fishing net is capture the magnetic field. So these are called a magnetic field net. Okay, because the fishing net capture fish, the magnetic field net capture magnetic field. Okay, the concept is. So there is some magnetic field. Suppose that B, suppose inside that fishing net, that P. That's the B, the B. Okay. Now we know from Ohm's law. From Ohm's law, we know that is B proportional to I. Okay. So here we see that there is a current, this induced current generated by when the magnetic field is varying. Okay. So here we choose a very small amount of area, very small amount of area on fishing net. Okay, and the direction is direction. That's the area. That's called a very small amount of area is called a differential area. That is a dA. B in that direction. There is an angle is theta. And the V proportional to I means from Ohm's law there is a I. If I is here, so obviously EMF potential EMF also here. Okay, so Faraday Henry experiment show that is a single coil are in relative motion or in one of the moving. So we get some current here, or suppose a tapping key when pressed or released, when you get some current, and these are called induced current. We know that from Faraday and Henry experiment for experiment 1, 2, and experiment 3. These three experiments show that the concept. Okay. So now the Faraday concludes is that the time rate of change of magnetic flux. The Faraday concludes that the time rate of change of magnetic flux, okay, through a circuit is induced EMF. Okay, induced EMF. Induced EMF. The time rate of change of magnetic flux through a circuit, okay, produce a induced EMF. Induced EMF. These are called induced EMF. So the induced EMF, the Faraday shows that as the induced EMF, okay, these are the induced EMF. Suppose these are the, okay, these are E epsilon. Okay, this epsilon shows the induced EMF, that is time rate of change of magnetic flux. So that is a d phi b by dt, d phi b by dt, and there is a minus sign, and there is a minus sign because they are in opposite direction due to the direction of the EMF. Okay, this minus came due to the direction of EMF. Okay, later you discuss why these are the minus and you get the answer. Okay, later discuss that, but there is a minus, this minus, because there is a EMF in negative direction. Okay, that's the opposite direction, say that. Okay, that's the, and due to the in negative direction of the EMF, that's why you get a minus sign here. And is another term is very important here for induced EMF. There is a number of turn in coil. There is a number of turn. Okay, this is a very important factor. There is a number of turn in coil. The number of turn is important for EMF. If more number of turn, here see that in d phi b dt means the more number of turns. So more number of turns, so that the more magnetic field capture inside the solenoid or a coil. You see that there is a, okay, front, and you see that is this magnetic field, this here to that point to that point, these magnetic field are captured inside the coil. Because if I say the less number of turn here, a turn suppose 2, so you see that this magnetic field is capture is very less amount. Okay, so more number of turns, so means that more number of magnetic field capture that the coil, inside the coil. So that capture now if magnetic field is more, so EMF is a more. Okay, so that's the final conclude that the EMF, Faraday law of induction shows the EMF, A unit of EMF is a volt, obviously. It is volt, keep in mind. Okay, so the EMF that is equal to minus n, minus so the direction of the EMF, that's the obvious opposite. The minus n, the d phi b of dt, that is change rate of change of magnetic flux. Okay, to a circuit. And now we discuss that concept is the direction of the current here. Ignore the direction of the current. Now we discuss what is the direction of the current, and that's defined by the Lenz's law. The Lenz's show the direction of the current. The Lenz law define direction of the current. Direction of the current. I. Suppose there is a bar magnet, that is a north pole, and here is a coil. Okay, and so that is a behind, that's the front part. Okay, there's a coil, and is bar magnet moving towards coil, moving towards the coil, and now they show the N. Okay, and if moving towards the coil means that here and let's go. Okay, so there is an N. So when you write down the N here, so means that that's the current direction, that's the I. Okay, so towards the coil we get some current I, and this current also produces a magnetic field. this current is also produce a magnetic field when you apply right hand thumb rule, and this magnetic field obviously oppose, okay, okay, this magnetic field B oppose this magnetic field. These also produce a magnetic bar magnetic field is oppose with direction of bar magnetic field. Okay, that's the N. And if towards the coil, okay, we show that it's an N. So suppose these are called anti-clockwise. So suppose see that is the anti-clockwise case. Now, if same condition is bar magnet away from the coil, so the away from the coil, suppose there is a coil and that's the back view behind the front. Okay, so that away from the coil, to write down S. S means is upward, that's current is downward. These are the I. Okay, the I direction. If the coil, or the bar magnet is away from the coil, we get a current direction but in opposite direction. The current are in opposite. So here the magnetic field, let's see that the magnetic field, okay, that's the inside. This induced current produce a magnetic field, and that is the same direction. And here when towards the coil, so magnetic field is increased, and away from the coil is magnetic field is decreased. Coil. Okay, magnetic field is decreased. And that's the Lenz law. Define the current direction. Lenz define the current direction. So if you want to write the definition right here, and that the polarity of induced EMF, the definition of induced EMF is such that tends to produce a current okay, which oppose the change in magnetic flux. Magnetic flux. Okay, that produce okay, and that's why EMF that is equal to minus n number of turn in the coil d phi b by dt. That's why you get a minus sign. Okay, this minus sign. That's a Faraday's law. Clear? And Lenz defines the direction of the current. Clear? What is the induction process and Faraday's laws of induction? If you have any doubt, please ask in comment section. I will give the answer. Next class we discuss a little bit more about that self-induction and mutual induction and these are process. Okay, in the process. So today in the class here. Thank you.